Hi there, this is Jacob Nash, and in this video we'll be reviewing how to find volumes using cross sections. So we can also use integrals to find volumes. And you might be thinking, well, why would I do that? Because it's just way easier to use a formula. Well, for one thing, it helps us to know how we even came up with the formulas in the first place. Um, because, it's kind of easy to find or know what a formula is of a 2D shape, but like in terms of area, but how did we ever come up with the volume equations? This shows us how, not to mention that sometimes have questions where it's not really a shape that it just might tell you two different graphs, and then you have to find the volume of that shape as if it was 3D. So uh, this will all make sense once we get to the example, but I'm going to try to just explain it conceptually first. So what does a cross section mean? Well, it means if we have a 3D shape, so like imagine if we had a cylinder and then we just cut it parallel, what shape do we get? Um, well, that's a circle, right? Um, so it's just basically the 2D shape you get if you cut through a 3D shape. So going the other way, if let's say they're saying find the volume here from A to L, which I don't know why it says L. I didn't come up with this, but uh we're seeing like what will this volume be if we made this 3D? And you can usually use three shapes. We'll talk about it. Semicircles, triangles, or squares. In this case, we use 3D. We're using semicircles, and I know that looks like it's just to the side, but imagine that it's up and sticking out. So it kind of looks like that. This is one way that we could do it. Um, and this is a little bit better right here. So as you can see, just like when we use Raman sums, we can get an over or underestimation, and this yellow part is like too much because that's just how it is, right? Like there's no shape that would really fit this region except for a semicircle. Well, semicircle we can use, but it is going to slightly overestimate. Um, and then if you're, whoa, sorry about that. If you're trying to find the volume of this part right here, volume is always going back to this. It's the area of the 2D thing times the height. So that's why the volume of a cylinder is pi r squared times h. This is the area of a circle times the height. So it's like multiplying it by the height is what makes it 3D. So same thing here, except for like we're pretty much calling it width, but same idea. Change in x. So we're going to do the area of whatever shape we picked, which as it says, doesn't have to be. We'll talk about like you can use different shapes. You'll just do whichever they tell you to do. Um, and if they don't have a suggestion, then do whichever is best. Sometimes it'll be better to do one thing than the other. So here's the area of a semicircle, and then change in x is the width. So setting this up in a Riemann sum, it would end up like this because we replace the r as the function. And you might be thinking, why? Well, as we move along on this, the radius of this semicircle will change. And we're using the left-hand side of it. But if I go right here, it's going to be a smaller radius, right? If I go right here, it's going to be bigger. So that's the reason why we make it a function. Technically, you could say or we could say r of x, but we still said f of x. So then putting into our limit definition, we have this right here. We're saying the area changes, so that's why we made it f of x instead of r, still squared. And then we made it this limit right here to say as the number of semicircles go to infinity with random radii throughout this interval, and we multiply it by the change in x, just like always, um, that will get us the exact volume of this region. So that is what that is. Um, Now let's look at it. Oh, um, this is supposed to be just the steps. So sketch a picture of of the region. So whatever it says, draw a picture if there's not already one. Find the formula for area. Hopefully you know what it is, like semicircle, triangle, or square. Then find where the curves intersect, just like we have before. And here are the three area formulas for the 2D shapes that you might use. Um, Square is just side squared. Semicircle is the same thing as a circle, but just one half. So one half pi r squared. And then triangle, one half base height. But just to let you know, occasionally they might make it to where you have to use Pythagorean theorem or trigonometry to figure out what the base or height may be because they're just stupid. But just as a heads up, if they tell you to use a triangle, that might be the hardest over these two. Let's look at an example, an actual example. We have a cone with a height of 5 centimeters and a base of uh, with a radius of 5 centimeters. Find the volume. Even if you know what the volume of a cone is, we're going to do it this way because this is how we get that formula. Um, so first, the step is to draw. So we're going to just make it sideways. That you don't have to do it like that, but that's what we're going to do. So as you can see, we end up having just a weird looking thing here. It's not really a specific graph. And then we have two lines here. And the graphs of these lines are x minus 5, negative x plus 5. I talked about in the last video how you would get that, but you really just look at what the slope is, and then we know what the y-intercepts are by looking. Um, and the radius is 5, that's correct. And then also the height is 5, that's correct. So that's good. Um, so now we have to create an area function, and all it is we do a of x, and then we set it equal to whatever area we need. So this is the area of a semicircle, but the reason why we made it Rx instead of just R is because the radius is not the same, so it's a function. Because as we move this red thing side to side to get this whole volume, like we're not wanting only this volume instead of the whole cone. So we move this freaking thing to the side and the radius changes. So uh, now we replace it with whichever we feel like because a cone is a mirror, so it doesn't matter which you use. So we'll just do this. So that's what we do. We replace with that. Now if you notice that there's the intersection point is here, and the same thing is always on the top, right? That's why I picked this one, but you could technically do that, but we'll just do this one because it's on top. And now we do our usual thing. This is our interval 0 to 5, since that was a height. And I put this 2 here because if we're using semicircles, if you can tell, like, oh, that's actually only half of the cone. So you have to go around the other side too. So then you might ask, well, does that mean I could have used circles? You could have. That was another option. There's usually more than one way to do things in this class, but semicircles are generally easier, so I would do that. But then you just have to remember to multiply it by 2 later, so it's not just half of the cone. Then we replace this a of x with the thing that's right here. Um, and then, oh, apologies, the 1/2 is not there anymore. I don't know what happened with that, but sorry, it's not there. But what you would end up having to do is FOIL this out, which is really annoying. And then you can do and maybe, yeah, you can FOIL that out, and then you take the antiderivative, and then once you plugged it into this thing, you would have gotten 125 pi over 3. And if you do know the formula, that's how you can check your work. So yes, it's a little bit tedious. The part that's actually tedious, I didn't even show, which is that you have to FOIL that out. But it's okay. You could actually leave that pi to the side. So it's not as hard, really, 1/2 pi, because like I said, that got missing. All right, let's look at probably more common example, because sometimes it's not always something that you would know the formula for. So it's saying basically find the volume between x squared and just the x-axis from 0 to 4. And it told us to use squares, so that's what we have to use. Um, and it wants us to do two things. First, perpendicular to the x-axis, then perpendicular to the y. Start out with perpendicular to the x. What does that mean, by the way? Well, it's unfortunately not really perpendicular, but it should be to this x-axis. So we draw the shape, and I know that doesn't really look like a square, but that's because it's supposed to be drawn 3D. But that's just basically one square, but we're imagining like we're moving that thing down the line to account for the whole 3D area. So just pretend like this is a weird 3D looking thing that's kind of like a door stopper, I guess. And the side lengths, you have to figure out the side lengths on that. It's x squared. How come? Well, think about it. This is the height right here. This is always going to be the y value, right? When you square it. So that's why it's x squared. And since it's a square, also the bottom part is x squared. So then once again, you plug this into the area function that it is x squared. So we do x squared squared because remember uh it's not it wouldn't just be x squared, it has to be x squared squared because you plug one of the side lengths into here, and this is the thing that you plug it into. So it ends up being x to the fourth. Now we plug it into here, and I'm not going to do that right now, but that would be you would find the antiderivative of this and then plug it in to find out what it is. Then if you're instead doing it with respect to y, it's a little bit harder. Um, and that means this time, or sorry, yeah, with respect to y parallel to the y-axis, that means the same thing. Notice this is perpendicular to the y-axis. Um, And you might say, how is this 16? Well, 4 squared. So 16. Um, so you have to figure out the side lengths. And the side length actually ends up being 4 minus square root of y. How do we know? Well, this is where it can get a little bit tricky, but we had to know that, okay, this full thing is 4. This thing right here is going to be always the square root of y. And the reason why is if we take this equation and we're trying to solve for y, or sorry, if we're trying to solve for x, because that's what we need, the x length, it would be the square root of y, positive and negative, but we only care about the positive. So that's why this is square root of y. Then how we got 4 minus square root of y is if the whole thing's 4 and this part's square root of y, then this is 4 minus square root of y. And since it's a square, that part's like that and that part's like that, even though this doesn't really look like a square. Sorry. Then you just plug this in, you find the antiderivative. I would recommend making that y to the 1/2. So you would really have to FOIL that out and then plug it in 16, plug in 0, and then you're done. Thank you for watching.